Hello everyone, I'm from Huawei Mass Data Storage domain. Today I'd like to introduce the OceanStor Pacific 9950, a high-density performance model from the OceanStor Pacific series. Specially designed for flash media, the OceanStor Pacific 9950 provides ultra-high bandwidth and IOPS to greatly improve data exchange efficiency in high-performance computing scenarios. This product houses 9 independent pluggable storage nodes in a 5U space, and each node is equipped with up to 10 NVMe SSDs. A single device provides a maximum of 160 gigabytes a second bandwidth and 2 million IOPS. Compared with the industry's highest performance density storage product, our OceanStor Pacific 9950 increases the bandwidth by a further 33%, and IOPS by 21% per U. Now let's have a look at how the OceanStor Pacific 9950 achieves such a high performance density. First, we have designed dedicated storage media for high-density flash hardware. These are palm-sized and half-palm NVMe SSDs. As the name suggests, a palm-sized NVMe SSD is as large as a palm, and a half-palm NVMe SSD is only half the size of a palm. Both palm-sized and half-palm NVMe SSDs are 9.5 millimeters thick, which is 37% thinner than traditional 2.5-inch SSDs. A palm-sized NVMe SSD is 79.8 millimeters high, while a half-palm NVMe SSD is just 38.4 millimeters high, which means that in addition to reduced thickness, there's also a 50% further decrease in height. This makes it possible for the OceanStor Pacific 9950 to accommodate 8 storage nodes in a 5U space with up to 80 NVMe SSDs. The half-palm NVMe SSD is equipped with an all-metal case made out of die-cast aluminium. This type of material has a thermal conductivity coefficient of at least 200 watts per meter per Kelvin. Truly high thermal conductivity, right? The internal flash and controller chips directly contact the metal case so that the heat inside a half-palm NVMe SSD is effectively removed. Compared with other materials, die-cast aluminium reduces the operating temperature of the flash chips by more than 5 degrees Celsius. Now let me tell you how we've solved the heat dissipation problem for our high-density system. As you see, high-density hardware contains multiple types of components in a limited space, and the heat generated by each component varies. How to dissipate the heat of each component is therefore a crucial consideration. Huawei has adopted some outstanding designs to deal with this issue. The first is the unique horizontal backplane design. A horizontal backplane provides communication channels between half-palm NVMe SSDs and processors with the advantage of minimizing the wind resistance in the wind direction. This increases the air volume for NVMe SSDs to achieve higher efficiency in heat dissipation. Secondly, we use carbon fiber pads and VC phase change heat spreaders to ensure proper heat dissipation for processors. Carbon fibers are characterized by stable, low thermal resistance and are often used for heat dissipation of precision electronic devices. Carbon fibers' thermal conductivity coefficient is 10 times higher than that of silicone grease. Therefore, they can remove heat from the processors more quickly. To better suit processor positions and air channel characteristics, we use industry-leading VC phase change heat spreaders with a capillary structure inside. Compared with the mainstream copper heat pipes and liquid cooling pipe, the VC phase change heat spreaders deliver higher heat dissipation efficiency to ensure that the junction temperature of a processor is lower than 85 degrees Celsius, which is 11 degrees Celsius lower than the temperature achieved by ordinary heat spreaders. Finally, we use customized counter-rotating fans to cope with a high wind resistance in the high-density system. Each counter-rotating fan consists of 2 rotors that rotate in different directions, and in this way, the wind produced by the first rotor is pressurized by the second to generate a high wind pressure and larger air volume, so that more heat is taken away from the high-density system. The OceanStor Pacific 9950 uses 32 counter-rotating fans with a diameter of 40 millimeters to dissipate heat generated by SSDs, processors, memory modules, and interface modules. By using all these heat dissipation techniques, we have successfully solved the heat dissipation problem for our high-density and high-performance storage. Next, let's look at how the OceanStor Pacific 9950 achieves high performance. First, the OceanStor Pacific 9950 is the industry's first all-flash storage system to adopt a full PCIe 4.0 design. Compared with PCIe 3.0, PCIe 4.0 doubles the bandwidth at a lower latency. The OceanStor Pacific 9950 supports multiple types of front-end protocol interfaces. Based on the application requirements, we can configure 100G EDR or HDR100 InfiniBand interface modules, or 100GE or 25GE Ethernet interface modules. Each node supports the 100GE backend storage network, and each port supports the RDMA protocol, meaning lower CPU usage and higher bandwidth. As we can see, the entire system adopts PCIe 4.0, and the front-end and back-end networks are independently designed. High bandwidth is therefore an inherent feature of the OceanStor Pacific 9950, which means it fully utilizes the performance of NVMe SSDs. Secondly, we use the distributed parallel client technique, or DPC, to accelerate performance. In the previous standard protocol architecture, one standard NFS client can only connect to one storage node. I/O requests from a host must be forwarded between storage nodes to implement cross-node data access. By contrast, DPC directly distributes I/O requests to the corresponding storage node to eliminate forwarding between storage nodes. This means a shorter data access path with more than 40% decrease in latency. Finally, let's look at how small I/O aggregation and large I/O pass-through are implemented and their advantages. If I/Os delivered by a host have a small granularity, SSDs will be frequently accessed, resulting in low data access efficiency. Our storage system aggregates small I/Os in BBU-protected memory based on a Huawei-developed algorithm. When the granularity reaches a specific value, I/Os will be stored on NVMe SSDs, reducing the latency by 70%. Large granularity I/Os are directly delivered to disks to double the bandwidth. We use a dedicated power backup solution for BBU-protected memory. When the device is powered on, the algorithm determines whether front-end application data will be stored in the specified memory space or directly delivered to disks. When the external power supply is abnormal, nodes will directly migrate the data in the BBU-protected memory to their SSDs for data persistence. After the power supply recovers, the backup power supply system will restore the data on the SSDs to the memory space, thereby ensuring data reliability. From this introduction, we can see that Huawei OceanStor Pacific 9950 uses brand new hardware and a next-generation parallel file system. Powered by all-flash media, the OceanStor Pacific 9950 is specially designed for high density and high performance. It uses techniques such as DPC, large I/O pass-through, small I/O aggregation, multi-level cache, and elimination of distributed locking to support both bandwidth and IOPS-intensive applications. With up to 160 gigabits of bandwidth and 2 million IOPS, the all-flash storage system provides you with the optimal performance. Facing the explosive growth of data, you need increasingly higher storage performance, but the space in data centers may be limited. Our high-density performance model, OceanStor Pacific 9950, is a great choice for you. That's all for today. Thank you for watching and see you next time.